In our follow-up video to the introduction to homeostasis, we're going to look at the two most common types of feedback cycles and see how each of these feedback systems are used in order to regulate and therefore achieve homeostatic conditions. Now, the first of which is a concept that we call positive feedback, and we can actually see this occurring anytime there is an exothermic reaction. Remember that an exothermic reaction is any reaction that releases energy as a product of the reaction itself. Now, whenever exothermic reactions release energy, this energy we would usually feel as heat, which means that there would be a corresponding temperature increase that occurs after this chemical reaction has occurred. Now, since temperature is just a measurement of the average kinetic energy of particles within this reaction environment, a higher temperature means that the average kinetic energy of all of the product and reactant particles in this reaction is also going to increase. Now, that means that if we just look at the reactant particles, if these particles are now moving faster, that means the likelihood that these particles are going to hit each other is also going to increase, and whenever we have a greater number of successful collisions between particles within a chemical reaction, that means that the rate of this chemical reaction is going to get faster as a consequence of this. Now, that means that if this chemical reaction is faster, that means that more of our products are generated, which also means that more heat is released by this reaction as well, which is going to increase the temperature, increase the number of collisions that occur between the reactants and cause the chemical reaction rate to get even faster, which means that this reaction is going to generate even more heat, increasing the temperature, causing the reactant particles to collide with each other more and causing the chemical reaction rate to get faster, therefore causing more heat to be produced, increasing the temperature, increasing the number of reactant collisions, causing the chemical reaction rate to get faster, and so on, and you get the general idea. So when we end up with an infinite loop like this, where the effects of the reaction cause themselves to get even more and more and more and more and more, what you have discovered is a positive feedback system. So if we want to conclude about what the results of a positive feedback system are, we say that the process or reaction that is regulated through positive feedback end up perpetuating itself. To perpetuate is a verb that means to go on forever, and that's how positive feedback systems work. As long as we have enough reactants to be able to do an exothermic chemical reaction, the heat that is produced by that reaction will feed back into the reaction itself, increasing its own reaction rate and thereby causing the reaction to burn faster and faster and faster and faster. And again, we use the word burn because this is literally a combustion reaction. And the only way to break a positive feedback system is actually to run out of the reactants that cause the reaction in the first place. Now, the second type of feedback system is the opposite situation, which is what we call negative feedback. And just as exothermic reactions can show us how positive feedback works, the opposite, endothermic reactions, can show us how negative feedback works. And the best example of an endothermic reaction, in quotes, because it's not really a reaction, all that we're doing is turning liquid water into water vapor. The best example of this occurs with human sweat. So we can see that this is an endothermic reaction because liquid water needs to absorb energy from the environment in order to evaporate and turn into gaseous water or water vapor. So what this means is that residual heat from the environment is going to be absorbed by liquid water, and when the liquid water's kinetic energy is increased and turns into gas water, this water vapor is not going to stick around. It's going to move away because gases have a higher kinetic energy than liquids do, meaning that this heat that was absorbed by the liquid water is going to be physically carried away by the water vapor. So if we dissect what exactly happens here, because the water in this case is absorbing heat from the environment, this is going to cause the environmental temperature of this reaction to decrease as a result. Now, as we know, temperature is simply a measurement of the average kinetic energy of the reaction system, and if we have less kinetic energy, that means that our reactants are moving slower as a consequence of this, meaning that there are going to be fewer collisions between reactant particles within the chemical reaction, therefore making it less likely that water would be able to absorb heat. And therefore, as a consequence of this decrease in temperature, we would expect the chemical reaction rate to decrease as a consequence, or to put it in more layman's terms, to slow down. Therefore, what we can see here is because we are taking heat out of the reaction system and causing that heat to be lost when this water vapor leaves the reaction system, this absorption of heat is actually going to slow down the chemical reaction and cause it to happen less. So negative feedback is much more subtle to see, but becomes obvious when we look at it in a certain way. The more an endothermic reaction happens, the more temperature decreases, which means the more likely the reaction is going to slow down itself. So we can conclude that negative feedback occurs when the process or reaction that's regulated by negative feedback naturally inhibits itself. So because of the decrease in temperature that results from the absorption of heat from the environment, this will naturally inhibit the process of absorbing heat from the environment and cause this reaction to happen less as a result. For a more tangible example, we can take a look at the process of sweating, because this is exactly the same process that is happening here. So as sweat evaporates and as it takes the residual heat away from our skin, we would expect that our skin temperature is going to decrease, and therefore our skin temperature is going to get cooler as a result. Now, as our skin temperature decreases, as we get cooler, that means that there is naturally less of a need for the body to sweat, because sweat is produced, or rather, water from sweat is released from the body in order to do evaporative cooling. But if the body is already cool, we have less need in order to release sweat. And therefore, we can see that evaporative cooling inhibits itself naturally as temperature decreases, and therefore we can see that sweat naturally regulates itself through a negative feedback process. In the next video, we're going to look at two specific examples of feedback cycles, not that doesn't occur with regulating body temperature, but instead occurs in a specific organ system and specifically regulates the amount of glucose that occurs within human blood.